Black holes are one of the most surprising objects predicted by Einstein's theory of general relativity. So in Einstein's theory of general relativity, space and time is dynamical. It can be bent by the presence of matter. And there are situations where you concentrate a lot of matter in a small region, and that can bend space-time so much that the notions of space and time get changed drastically compared to what we are used to. For example, when a black hole forms, there is a whole region of your space-time that cannot send signals to the outside. So no matter what you do, if you find yourself in this region, you cannot come back out. You cannot even send a signal. In some sense, that in theory is to the future of everything that is happening outside. And for that reason, you cannot send signals in the same way that you cannot send signals to the past. So that's a weird aspect of black holes. So somehow this interior is to the future of everything else that is happening in the universe. That's what classical general relativity predicts, what Einstein's equations predict. Once you consider the effects of quantum theory, so quantum mechanics is another important pillar of our understanding of nature. Quantum mechanics has small effects on black holes, but these small effects have drastic implications. These effects is what made Hawking famous. So he did a calculation where he found that quantum mechanics implies that black holes emit thermal radiation. So they emit radiation as if they were hot bodies. It's a bit strange. I mean, you start with this picture of Einstein where space-time, let's say, is like a membrane that can be deformed, and so you can have these big deformations, and then suddenly you find that this big hole becomes hot. So now, why is this strange? It's a bit strange because we associate temperature to the motion of some constituents of matter. So, for example, we feel the temperature of the air in this room because the molecules of air are hitting our hands and so on. The faster they move, the bigger the temperature. If they were not moving, we would have zero temperature. Now, in the case of the black hole, so the matter has fallen into the black hole, and we only have a configuration of space-time. Configuration of this, in this picture, is like a membrane. Of course, it's more dimensions, and only space-time is involved. It doesn't matter what formed the black hole, what kind of star formed it, and so on. The temperature is universal, and we think that this temperature has something to do with the motion of spacetime itself, the atoms of spacetime. In the same way that understanding the temperature of a gas involves understanding the motion of the molecules, understanding deeply the temperature of black holes involves understanding the motion of the atoms of spacetime, roughly speaking. So the goal is to resolve these paradoxes and find what the full theory of spacetime at the quantum level, so a picture of spacetime where you understand what these elementary blocks of spacetime really are. And the black hole problem is like a test lab for these ideas of quantum mechanical spacetime. Why am I talking about the theory of the quantum mechanics of spacetime? Why do we need this? It's not very important for our everyday experience, because in our everyday experience, we either apply gravity or we apply quantum mechanics, but we never are forced to apply both at the same time. The place where we think we should be forced to apply both at the same time is at the beginning of the Big Bang. At the beginning of the Big Bang, we cannot apply either quantum mechanics or gravity. And the reason is that quantum mechanics applies for very small things, and gravity applies for very heavy things. But in the beginning of the Big Bang, the whole universe was contracted into something very, very tiny, and we need really both things. The black hole problem is a test problem for this for the quantum mechanics of spacetime. It's a bit simpler because in the case of the black hole, you can sit far away from the black hole, and well, nothing very bad happens to you. But if you, at the beginning of the Big Bang, you had time that suddenly appears, or we don't know what happened before. The questions are a bit more confusing. And we think that the black hole problem might be more within reach than the Big Bang problem. But well, that might turn out to be the other way around. We'll see.